certain trends that be happening over and over and over again. And so that way we can see the fact that they're very similar to what you've seen in organic chemistry, or if you're currently in organic chemistry too, what you would be seeing in organic chemistry too. So there's only certain types of reactions that can occur. For whatever reason, like we can't, I mean, it won't even come on, anything like that, and so. And I can't even get the green light, like it never turns the green, and it won't even let me hit like video on or off, and I've tried turning it off and turning it back on, and. All right, so just like organic chemistry, you're going to see like redox reactions, you're going to see things that would make carbon bonds or break carbon bonds, and the one problem is, and usually at this point in time, especially if I was teaching both organic chem 2 and biochem 2, is we give the example of, you know, and you don't have to write this down, but just to show an example, which I probably should use this hand. You know, there's a way, you know, to turn an alkene into an alkane, right? And the only difference here is this is hydrogenation reaction, and what, does anyone remember what the catalyst was from organic chemistry? No, it's like platinum, palladium, nickel, rhodium. Those, obviously we do not have platinum electrodes inside our body, or what's this shit, unless you're some type of like, you know, android or something like that. But no, you don't. So our body has to utilize something else to get around these same organic compound, you know, organic chemical reactions that occur. And so many times these are the cofactors and enzymes and coenzymes, especially coenzymes and cofactors that you hear, your vitamins that you hear about that will do these kind of things that help it out as the catalyst, okay? And so you need to look for these patterns. Do not try, please do not sit there and try to memorize every single reaction we ever come across, because it's almost impossible to be able to do well, okay? So on your own, this is where, and this is on the slide, I actually have on your own, there are a couple of things from chemistry and organic chemistry. One of them is just types of chemical cleavage that occurs, ways to break a bond. And so there's homolytic, which means it's broken evenly, versus heterolytic, okay? Which is where the bond, both electrons in that bond goes to one atom. So you'll have one that's negatively and become an anion, one that's a positive or cation, okay? That's because it's broken, it's not the same. This is whenever you make free radicals. And then finally, this one's even more important than that other one, and that's nucleophiles and electrophiles. Which, what are nucleophiles? They go and they attack, and what must be present in order for it to be a nucleophile? Lone pair electrons. Now, it doesn't have to be negatively charged, but you have to at least have lone pair electrons. Electrophiles are what? They electron loving, okay? So what else are they? Nucleophiles attack. They attack the electrophiles, right? So because they love the nucleus, they have extra electron density. This one is lacking electron density. So some examples, this is just one example that we have. Of course, this carbon here is an electrophile because it's delta plus, remember from the delta minus. The nucleophile, whatever it may be, one example that we see in vivo would be like an amine, right? That can come in and attack it. And if you remember from organic chemistry, boom, sound effects optional. You know, you can break that bond to form a tetrahedral intermediate, and so on and so forth. So this would be the nucleophile, and that would be the electrophile. And so, and then, and this came directly from you. Actually, I think we actually already had this exact figure early last semester when we did this. And it's repeated in this chapter where it gives you examples of both nucleophiles and electrophiles. And electrophiles that are important in vivo, the ones that we see over and over and over again, are carbonyls, so the acyl groups, those, or imines, which remember, imines is a functional group that we do in biochemistry, but we just barely touch upon in organic chemistry. What's an imine? Okay, that's a carbonyl or acyl group for like a ketone, aldehyde, carboxylic acid, amide. But what's an imine? Do you remember? What does it sound like? An amine. So it means it's got a nitrogen. But what makes it an imine? Double bonded. Okay, and of course remember, nitrogen actually has 3 bonds and lone pair electrons. And so once again, the carbon is delta plus. It gets attacked, that bond can pop off. Sometimes, especially the imine, sometimes these are also called, biochemistry loves this term, I don't think they use it too often in organic chemistry, which is a shame. They're called electron sinks. Yeah, because the electrons will bang into that carbon, they'll sink in, and so it flows towards the nitrogen or the oxygen. Okay, so they're called electron sinks. And there's one in particular, an imine called the Schiff base, which we'll see later on. Okay. Wow, we stumped him. I've never seen Jonathan stumped before. So, there are 6 types of reactions, of biochemical reactions. They all have to fall under one of these 6 types. I'm not talking about the enzymes. These are just the types of reactions. Now, they are not necessarily mutually exclusive. Sometimes you can have the same enzyme mechanism more than one type of reaction. Okay, 6. Oh, 5. I miscounted. 5 types of reactions. I would have caught myself in a moment. The way previous classes remembered them was the little, and they're in a different order than it's on here, is iFrog. I don't remember why they came. I mean, if you can think of some other way, but iFrog is the way that they did it. So the I was for internal rearrangements. So good examples of this would be like isomerization reactions and group transfer, like moving an alcohol from carbon 2 to carbon 3, for example. So these can include isomerizations from one isomer. Isomerizations. Okay. F was free radical. Okay, so free radicalization or free radical reactions. You don't see these, well, many times in vivo, this would be an intermediate. Why would you not want this as the final product? Free radicals will go out and they'll destroy everything and you die. Okay, we die frequently in biochemistry. So bad things happen like cancer and so on and so forth. They're still important, and we're going to find out some things like some of your B vitamins like cobalamin. One of the reasons why it's so important is it can literally remove radical groups by doing that homolytic cleavage. It can just move it over without that free radical ever popping off. Okay, and we talk a lot about electron transfer when we do electron transfer chain. One of my favorite proteins in the world are the hemes, just because it has the only job that it has is whenever electrons sometimes spew off, because it's going so fast, it's going like 100 to 150,000 times per second. It's going so fast that there are times, contrary to the way that I would always say in organic chemistry, an electron really would spew off and would hit some other atom. There's one called heme B, and all it does is it catches it and spits it back. And so I call it's my catcher from from baseball. So it's there right next to where the electron transfer is occurring, and it catches and it spits it back, catches and spits it back. All right.
Like a very direct thing, it just puts it back.
It just puts it right back into, because you'll find out there are 2 players that's right there that transfer the electrons from each other, and because you have to be able to transfer these free electrons, the electron flows, that's why it's an electron transport pathway, electron transport chain. And so it's there, just what happens when things go wrong, because it's one of the backup plans. Oh, awesome. All right. I have to give it positive reinforcement sometimes. Awesome. Then, like I said, this is not in the order of iFrog, the order that I have here, but the R stands for reaction. It's the one that's always the hardest for me to remember. Reactions that make or break carbon-carbon bonds. Okay. I think they like the R part for it instead of C or N or B, just because otherwise you couldn't have an iFrog. All right. The O is oxidation reduction reactions. Your redox reactions. So we'll talk about that in great detail. And then G is your group transfers, but not internal transfers. We're talking about transfers from one molecule completely to another molecule. If it's internally, then that's going to be a rearrangement, that internal rearrangement. Like if it's just an alcohol group, which we see that like phosphate going from carbon 2 to carbon 3 from within the same compound, that's not considered a transfer between, since it's all in the same molecule.
A group transferase, is that like the acyl?
Like acyl transferases, aminotransferases, hydroxyl transferases, sometimes they're called hydroxylases. I mean, there are lots and lots and lots of examples of them. Like the next slides, we went through, and actually I've already mentioned this, and so that's why I'm actually not going to even spend a lot of time on any of these, just to point out, because we've already mentioned it, the reactions making and breaking carbon-carbon bonds, making and breaking them, ones that we utilize the most are that carbonyl and that imine, what we talked about over there, okay, with nucleophiles and electrophiles. So that's a way to add things to the carbon, or to break it down. If you remember from organic chemistry, you can have that collapse of a tetrahedral intermediate to kick off something, kick off a leaving group. Okay, and so that's a good way of doing making and breaking carbon bonds. These are just some of the examples. Oops. Actually, go all the way through and show it this way. And so here, and these are some of the proteins that we're going to enzymes that we're going to come along throughout the semester. So first off, we have an aldol condensation reaction, which if you remember from organic chemistry, an aldol just means it has some type of acyl group and an alcohol on it. And we're going to see this as an example would be aldolase, which is in glycolysis. You can have Claisen condensation reactions. Now, many times for us, in vivo, we use coenzyme A. Sometimes I abbreviate it as CoAsh, because that's the way it's abbreviated a lot of times, because it's got a sulfur in it, and it's one way, and we'll talk about that later today, hopefully, about the reason why sulfur gets used instead of oxygen. But citrate synthase, which, just as a quick review, synthases, what do those enzymes do? They synthesize, and so what do you suppose citrate synthase synthesizes? Citrate. That's part of the citric acid cycle. And then we have beta-keto acid decarboxylation. And if you remember from organic chemistry, this is called a beta-keto acid, because that's carboxylic acid. Maybe that's called, I call it the ground zero carbon. That's C-alpha and that's C-beta. So it's got a keto group that's beta to that. And we're going to see that over and over and over again, especially towards the end of the semester when we talk about a lot of the neurotransmitters and their biosynthetic pathways, especially those derived from amino acids. For example, histamine is due to this kind of decarboxylation kind of thing. Or those are decarboxylation groups. Or we see it actually even more quickly than that. We'll see that with respect to fatty acids, like the breakdown to get energy and stuff like from fatty acids. It's probably a better example. Internal rearrangements. One thing to point out here is that overall they can't affect the oxidation state, because otherwise it would be a redox reaction. Okay, but that should make sense. When we say an internal rearrangement, it's literally moving a group from one carbon to another carbon, like switching places. Okay, here I'm gonna go through all that. Okay, so this is an example of an elimination reaction that doesn't alter the oxidation state. So these are condensation reactions. Okay. And this is just an example. Once again, we'll see these over again later on in the semester. This is fumarase from the citric acid cycle. Then we have the free radical reactions. These are important in vivo. One, I already mentioned cobalamin, which has to do with vitamin B12. Okay, so they are type of isomerization reactions, but they involve the formation of a free radical in the intermediate steps. Okay, and this is our good friend Sam, which is also called adomet, which to me sounds like something from Star Wars, because it's adenylylated thionine. So a lot of times they'll abbreviate it and they call it adomet. I prefer Sam, but this is the same thing. Then there are certain types of free radical decarboxylations, and then, as you can see here, photolyase, which has to do with DNA, and then also some RNA metabolism that utilizes free radicals. Group transfers, I mean, there's so many, I couldn't go through them all, but anything, literally, means it transfers from one compound to another. There's kinases would be an example of this. Whoops. Glycosylases, acyltransferases, aminotransferases. Like I said, there's so many that we could. All right. Usually, this is just one example. So this is just a review from organic chemistry. You've seen before, you had your nucleophile, something coming in, smacking the electrophile, boom, sound effects optional. Something had a break or give, so you'd form the tetrahedral intermediate. You get collapse of that intermediate, and it would kick off whatever the leaving group was, the X. You see that over and over again. It's a tetrahedral intermediate, and that's whenever there's an acyl group that's involved. But that doesn't explain phosphates. So we see this a lot with esters and thioesters. What's the only difference between an ester and a thioester? Sulfur. Instead of that oxygen that links the acyl group, it's just sulfur. And we talk a little bit about that later on, about the reasons why. But thioesters undergo the same type of tetrahedral intermediate, the same reaction mechanism over and over and over again. That's not true with phosphates. Phosphates are very, very important. We're going to see that over and over and over again. We don't get to talk about this in organic chemistry, usually, at least whenever I taught it, just because of the fact that it's not covered in greater detail, and or it's just skimmed over. But phosphates have a huge amount of resonance structure. That's why phosphate itself is relatively stable. It's very stable because of all the facts that there's resonance. But what happens here is that since we're starting off with something that has 4, so we would have the R group that would be attached. Where's my pen? Instead of this being a minus, there'd be an R group right there, okay? And so what happens here is when the nucleophile comes into attack, there's already 4 things attached. But we see this double bond, so you can still break the double bond to form the intermediate, and then you get collapse, and you kick off, if there's another leaving group, then you can kick off that R group, for example. So what it does is it's a pentacovalent. Instead of tetravalent, meaning there's 4, it's got 5 things. Otherwise, it's the same thing. Here they're just showing you, they're showing a specific example, but they're just showing you have that nucleophile or something coming in, you have the leaving group leaving. Since there's 5 things, it's pentacovalent. This is one specific example here. We have a nucleophile from the glucose, smacks a phosphate. You temporarily get that pentavalent intermediate, you get collapse, and it would kick off an ADP. And now we actually have glucose 6-phosphate. Okay. And so if we look at this enzyme right here that does this, what class of enzymes is it going to fall? This is also a good review. What class of enzymes is it going to be? Because we're transferring a phosphate. And it's usually utilizing ATP, and so what? It's a kinase. This, by the way, is hexokinase, but yeah, this is a kinase. And finally, we've got our redox reactions. In vivo, we see the whole gamut of the oxidation states of carbon, all the way from the most reduced. Remember the cheating way, I shouldn't say cheating because it works, but the easy way to tell if something's being oxidized or reduced, if it's being reduced, you are increasing the number of carbon to hydrogen bonds or decreasing the number of carbon to oxygen bonds. If you're oxidizing it, you're increasing the number of carbon to oxygen bonds. And so that's why the most reduced is an alkane. You can make it into an alcohol. It becomes an aldehyde or a ketone. carboxylic acid, and then in the most oxidized form, it's carbon dioxide. And so our body utilizes every little bit of energy that it can get. So when we take that saturated fatty acid, okay, yes, it's got one end that's going to have that carboxylic acid on it, but if it's a saturated fat, if you remember from last semester, it means it's all carbon, hydrogen, single bonds with that one terminal. And so literally what our body does, so if we had something that looked like this, whoops, those are supposed to all be single bonds. It breaks it down 2 by 2 through all of these steps essentially. Well, it doesn't go directly from alcohol to aldehyde. I mean, we actually will learn how it does that in order to get every single bit of electron energy out of that. It completely will oxidize it down to carbon dioxide. So that's how we get all this energy from those fatty acids and from those fats that your body eats or stores, in the sense that we completely will oxidize it down to carbon dioxide.
So that goes all the way down to carbon dioxide.
Oh yeah, that's why if we inhale, we exhale, then we just exhaled completely, oxidized forms of energy because our body, if you're healthy, then your body is doing that, of course. All right. You can't have one with the other, it's like a yin-yang kind of thing. If something is being oxidized, something must be reduced. Right? You can't have one without the other. Usually, when we talk about oxidation, we're talking about some type of energy release. Now, these are the big hints. Many times, you're going to see these cofactors. There's NAD, NADH, because one's oxidized. This is the reduced form, that's the oxidized form. FAD, FADH2, that's the reduced, that's the oxidized. Note, this one says positive on it, this one does not. The other one that you'll see sometimes, it's related to FAD, is FMN. It's also, the F stands for flavin. And then its counterpart is FMNH2. Enzymes that utilize these are almost always called dehydrogenases. So that's why this is just showing you lactate dehydrogenase, which, by the way, lactate dehydrogenase in humans, it utilizes NAD, NADH. Okay. The next slide doesn't work very well on the Mac because I've got all the different parts on here. So on your own, but it does show you here FAD, FADH2. The little part that's in the box is only different. So it's only in the box is FMN. But then we're just talking a little bit about the cofactors that are involved. All right.
You said the enzymes, so
Dehydrogenases do redox reactions, oxidative reduction reactions, utilizing the NAD plus NADH or FAD, FADH2, or in theory FMN, FMNH2. In humans in vivo, we don't use FMN very often. We usually use the adenylylated one, which is the FAD. Yeah. Just like there are other oxidases, reductases, oxidative reductases that don't utilize those. And those typically are called oxidative reductases, whereas if they do utilize them, they typically are called dehydrogenases. So like kinase versus what's phosphorylase. Mm-hmm. Once again, sometimes you have some historical carryovers, but if you just had a guess on the MCAT and you saw that there, you could guess that's a dehydrogenase. And then chances are you're going to be right. All right, so why use ATP in phosphate-containing molecules for our energy source? And the reasons why is because it gives off a large negative free energy change. Remember, delta G has to be negative in order for it to be energy given off. And so what happens is we can couple that to reactions that are unfavorable in order to overall get energy released. So it's sort of like, making, have to invest money to make money kind of thing. And so if you think of ATP as our energy currency, if you're trying to do a reaction that's energetically unfavorable, but you couple that to the hydrolysis of ATP, overall it may make it negative. Okay, which remember, negative is positive. Negative is advantageous here. Okay. ATP can be cleaved at multiple locations. We'll show that. ATP is not the highest energy source, though. Your body actually utilizes other energy sources even higher than ATP that's phosphorylated. Sometimes I have asked that, if you think about why don't you use the highest? Sometimes, or I've done that even that, kind of as a little thought exercise, like you hypothesize, why doesn't our body use the absolute highest as the energy source? Just to see what you guys come up with, but I don't know if I'll do that or not. It's a little tempting thing, like just say, why don't we use the highest one, like phosphoenol pyruvate, which is called PEP. Okay, so this is just an example here to show you how ATP, this is like for a phosphorylation, like a kinase kind of reaction, because it's doing the terminal phosphate. But you can also attack, instead of attacking this phosphate, we could have attacked this phosphate, and instead of giving off ADP, we'd be giving off AMP. In theory, you could attack this phosphate and give off just the sugar, the ribosylated sugar. Sorry, the adenylated sugar. Or, in theory, you could also connect the carbons here, but that doesn't happen. And so that's why there are multiple places. We have 1, 2, 3, and in theory, 4 places that could possibly be attacked. There is resonance stabilization, so that's why inorganic phosphate is so stabilized with respect to that. And you also see all these negative charges by each other, and you can also relieve some of that repulsion. So that's why there's so much energy. You get negative 30, almost negative 31 kilojoules per mole for every ATP. Okay. Here's another little hint, like a little factoid to keep in mind. Anytime you see phosphates involved, almost always magnesium in vivo is the cofactor that you're going to have. Sometimes the enzyme won't even work without it. And the reason why is because there's so many negative charges. Magnesium, it's called chelate, can chelate to multiple oxygens, hold on to multiple oxygens at once. So if you just have a guess, you see there's an enzyme, and if you see that they're moving a phosphate around, or it utilizes ATP or GTP or any of those, you want to write down magnesium. It's going to require magnesium. I'm sure that there's some examples that maybe would use calcium or whatever, but 99.99999% of the time probably, I would say, is magnesium. Okay, so it's what? Because you have to have something positive there. And in vivo, that's why if you remember back to last semester, early on last semester, when we talked about the standard conditions for biochemistry versus organic chemistry, or gen chem, for general chemistry and organic, you had to have 1 molar of everything, pH 1, essentially. You had to have, it just didn't make sense. The temperature was, 25 degrees, by 25 degrees, which for biochemistry is 37 degrees for the temperature, because that's our body's temperature. But one thing that we have for standard conditions is magnesium. Your body has to have some magnesium in order for the reaction to occur. These are just examples just to show you the fact that ATP is not the best, all right? So ATP to go off inorganic pyrophosphate, you actually get off even more energy than you do if you make ATP to give off ADP. Okay? This is done by inorganic pyrophosphatase, which I mentioned before. This inorganic pyrophosphate. So you can imagine if you start off with ATP and you kick off this, you get negative 45.6 kilojoules per mole. Then we have an enzyme that comes along, kicks that apart, and then we're going to get another negative, so you can get even more energy that way. But if you look just PEP, this phosphoenol pyruvate, we call it PEP for PEP, it gives off the most. Okay, but we see PEP is made in one of the steps in glycolysis, and you also see it in gluconeogenesis, but it's not the main energy source for us, for energy currency.
Doesn't it use like enolase and everything before?
So yeah, we'll talk about enolase and we'll talk about pyruvate kinase and some of these.
Okay.
All right. And then normally we would spend more time about why is it that these are even better. This is just one of them. We can see, remember that was the term, was tautomerization. Resonance, anytime you have resonance, they have even higher, better resonance than ATP, then it's going to be, this is phosphocreatine, the guanidino group, and then we have, 1,3-bisphosphoglycerate, which a lot of times we will see these, but they're just not the main go-to energy source for glycolysis. Okay, that's, those are ATP based.
So you said that phosphoenolpyruvate is best because of resonance?
Right, it's called tautomerization. Remember, it can go from the enol and the keto forms, something that we see with enols. All right. This is just a little example here, because you're going to see this over and over and over again in your book. They'll show a phosphorylation, or they'll show this kind of reaction, to where it's shown as just one step. So, for example, this one is, not glutaminase, glutamine synthetase. Okay, and so it utilizes an ATP, but notice the phosphate's not in the final product. So what happens here is it may be shown as just a single reaction, but in reality you have to remember it's a two-step. First, it gets phosphorylated, then the nucleophile comes in, pops off the inorganic phosphate to get the final product. And the reason why is this phosphate, remember, is a much better leaving group than just an oxygen. If you think way back to organic chemistry too, you could even talk about the fact that, amides are better than carboxylic acid. This is a carboxylate, so that's why an O- would have to leave as an O2-. It's not going to happen. So the only way for it to happen is we have an enzyme that first phosphorylates it, then it kicks off as an inorganic phosphate to be able to add that nitrogen on. Okay, I already mentioned that. That just shows you where I mentioned it. We actually already talked about the different kinases and stuff, so you can on your own review that part. All right. And I just want a little bit discuss in the last couple minutes sulfur. Okay, so this is the whole idea of why our body utilizes thioesters rather than just oxygen-based esters. We talked a little bit about it last semester, but we're going to go in greater detail. And you're going to see coenzyme A, you see a lot this semester. And like I said, a lot of times it's abbreviated. If it's free coenzyme A, they abbreviate it as CoAsh, because that's coenzyme A and it's got a free thiol. If it's acetylated, they may even call it like acetyl-CoA. Technically, this one's acetyl-CoA. We see all of this portion right here. That is not used. It is used. It's important, but it doesn't do the chemistry, right? So maybe it's used for binding or for the enzymes to recognize it, but the important part of this entire... Whoa, that's really big. I didn't mean for it to come up that. Let's see. It's right here. Okay? And so rather than using an oxygen at this place, our body utilizes a sulfur. So that's why coenzyme A, when it's free, it's got a free thiol. Otherwise, and it doesn't have to just be acetyl group. It can also be acylated, meaning it can have fatty acids or just anything that's got a carbonyl group on it. Okay, so that would be called a formylation if it's just adding an aldehyde, but it could be it could be something really huge, something like this, and then I'm just going to go ahead and put CoA because that's how we abbreviate it a lot of times. Rather than drawing all of this out, we abbreviate it CoA. And so that's why I'm saying this now. What our body would do is it could transfer this entire fatty acyl group onto a protein, onto something else, okay? Because we have that sulfur there.
The ch13 would just be an H.
This just shows you the hydrolysis of acetyl-CoA. So here's where, see, that's showing you it's free coenzyme A, and it's abbreviated as CoAsh. This is the reason why energetically, and I really like this figure. I think I also show it, a lot of times I even show it in Biochemistry 1 when we talk a little bit about this. What happens here is if you think back to organic chemistry, esters are actually relatively low in energy because there's resonance. It's not great resonance, but there is resonance between these two oxygens. So that double bond is shared. Sulfurs can't do that. So it's higher, it's actually higher in energy. So what happens is it's easier for a nucleophile to come in, attack that carbon, and pop this off because it's already higher in energy. At the same time, sulfur is a better nucleophile than oxygen. So it's a better leaving group and a better nucleophile than oxygen. So that's really, really nice. Your body utilizes sulfur because it's reversible. Oxygen, if we only use alcohols and esters, is much more difficult because the esters are already kind of happy. So why would you break that all up? Oxygen's not as good of a nucleophile. It's not a horrible nucleophile, but it's not as nearly a good nucleophile as sulfur. And so that's one reason. So there are two reasons. One, I mean, the easiest way to say it is sulfur's a better nucleophile, but sulfur's also a better leaving group. And this is just showing that leaving group. Okay, so I'm going to go ahead now.